down if you don't want to, because actually writing isn't what I would prefer you to be doing. I would prefer you to be thinking. And if writing helps you think, great, but studies have shown you should write very, very few, perhaps no words and just little pictures, or really do your writing after class would be even better. So, okay, so that was basically the most important things. The only other thing from 6b was the Rees representation theorem, which says that every linear functional is, or maybe I'll say it, for every linear functional, there is a unique vector such that phi of v is just vu. So basically this means that v is isomorphic to v dual. For every linear functional, there is a vector, and the pairing is that you create the linear functional by doing, in other words, sort of phi is equal to open slot u. And you see that this is linear because the first slot is linear. First open slot is linear. And this is, of course, false, but it's true if dim v is less than infinity. If your vector space V is infinite dimensional, then there are many interesting things like the Dirac delta quote function. It's not actually a function. If you want, you can look up distributions. You can look up Green's functions. And if you don't want to look them up, you can take PDEs next year. Next fall 2026. Okay. Questions on 6b? That was a review. Oh, there was one other thing that was important from 6b. How do I get an orthonormal basis? And we practiced that last time, so yeah. Okay. Let's move on to 6c.
Can you show the isomorphism part one more time?
The isomorphism part. Yeah.
We don't know that this is an isomorphism yet. We haven't proved that it's surjective.
We would, so in the book they prove everything you need. They just don't maybe say that it's an isomorphism.
Because we definitely proved that in this section.
Oh, we did? Okay.
I don't know. I don't remember if we did in the last section.
I think everything you needed was probably there. Yeah, yeah. Because once you have, for every linear functional, there's a vector, and it's unique, and so, yeah, you have to check some details.
Yeah.
You're right. Yeah. Okay. 6c. What is u perp? Well, also, the way we say this is u perp for perpendicular. So I could say it in words first. How would somebody like to try to say it in words? U perp is
all the vectors
That's how I would start. All the vectors that are something to you. What did you say? Perpendicular to the entire subspace U. Meaning like, here, let me just write what you said. All vectors in V that are perpendicular And here's what I would add: to everything in U. To everything in the subspace U. So like as a set, we could say all the V's in V such that UV equals 0 for all U in big U. Yeah, as a set. Yeah. And then the most important use of this set will be that we can now break up the entire space V into a piece of U and the other piece is U perp. And this works if the dimension of V is finite dimensional. Okay? I think. I can't remember. So how do we prove this? Theorem. Well, if you take V, so given a vector V, little v, nobody can stop you from writing U equals a sum of the V EJ where E1 through EK are an O and B of U. Okay. So maybe this is where we need the finite dimensionality, at least of U. Do you see what? Do you remember the book made a big deal about finite dimensionality? It's because some things are false, if you forget that. Yeah. No?
Given a vector, is that U or V?
Given a vector V, nobody can stop you from writing U equals. So what you should notice is this is the projection formula. These are like, look, if you're going to use coefficients, like those have got to be the coefficients. But the key here is that I don't have an ONB of the entire space V. I just have an ONB of U. And so I think actually what you need is that the dimension of U is finite, so that you can construct an orthonormal basis. Yeah. If you have an infinite dimensional vector space, maybe you can't always find an orthonormal basis. I don't know. Because Graham-Schmidt is sort of like, you'd have to just keep going. Will you ever finish? Right? You see how that works? Graham-Schmidt, we just have to keep picking vectors that aren't there, but we need to finish. If we don't finish, we don't have an orthonormal basis. So, yeah. Okay. Now, why am I'm not done yet. Note that V is equal to V plus U. Oh, no, wait. It's better to write it like this. V is equal to U plus V minus U. Okay, now this is one of these things in math that we do quite frequently, is we write something and you plus it and then you minus it. This happens in Math 200 when you were doing some proofs with epsilons and stuff. Now it's happening again here. And the key is that obviously this little vector U is in my subspace, which, this is clearly U is in U, because it's a linear combination of the basis of capital U. And now all I have to do is show that this piece is in U perp. So question mark, is it in U perp? And then what I've shown, if I can show it's in U perp, that implies that my big V is equal to my big U plus my big U perp. And then, do you remember that U and U perp intersect in 0? Because if you have a vector in U and it's orthogonal to everything in U, that means it's in U perp. It has to be a 0 vector by the properties of inner product. So U and U perp cannot overlap. They can only overlap in the 0 vector, because if there was something in the intersection of U and U perp, it would be in U, and it'd be orthogonal to everything in U. In particular, it's orthogonal to itself, which means it's a zero vector. So, because of that, then we're actually done, and we've got a direct sum. So all I have to do is show this piece, that it's in U perp. And how will I do that? I will switch to a different color, and I will take V minus U, and I will dot product it with EJ. And this is, I switched to a new color because this is a big idea. In linear algebra, it is often much easier to just check something for on a single basis vector at a time. And then by linearity, you've got it on the whole thing. So I have to show that V minus U is in U perp. That means I need to show it's orthogonal to everything in U. That's infinitely many things to show. I don't want to do infinitely many things. So what I will do is I will do it one basis element at a time, and then anything in U is a linear combination of these, but the inner product is linear. So all it will depend on is whether these are at 0. So I'm going to show that this is 0. This blue thing that I wrote, I'm going to show it's 0. Question mark. Well, what is it? Well, by linearity, it's V EJ minus U EJ, right? Question mark equals 0. But what's U? If I look at, do you see what U is, little u? If I dot it with EJ, all the terms are going to 0, except the EJ dot EJ will be a 1, leaving the coefficient, which is VEJ. So this is VEJ. And what's a number minus that same number? For example, what's 5 minus 5? 0, yeah. So we're good. Okay. Questions on this? Are we good with U perp and this direct sum? By the way, I'm recording this, so I'll post it on YouTube in a moment. And I'll put it on Canvas.
Can you explain that last equals one with the UEJ equals VEJ?
Yeah, so this one I did in my head. I'm going to take U and hit it with EJ. And so I go over here, this is U. If I hit this thing with a single EJ, it's going to zero out all the terms that aren't the same EJ. All of these terms are going to 0, except the EJ.EJ term, which goes to 1,
Nice.
and just leaves that coefficient. So, that's nice. And now, but psychologically, what I think of is that, why is this a direct sum? Well, because I can orthogonally project onto U. These have to be the coefficients, right? We already knew from section 6b that we reviewed a moment ago. These are the coefficients. If you're going to project onto U, this is an orthonormal basis of U, these have to be the coefficients. And any part of V that was elsewhere is just not here anymore. I'm just not writing it down. And it's this piece. This is the part that wasn't in U. This piece is the orthogonal piece. So it's just like my picture that I wrote a moment ago with the triangle, where this vector is my U and this is my V minus U, which is at 90 degrees. And that's what we just proved. Okay. So you see this triangle picture is important. Okay. Next up. What's the next important thing? Ah, very, very fun. This is the next important thing. Say we want to solve, and yeah, I am lecturing today because I just think that this is a tough section, and I think that I can actually make it pretty easy. So that's why I'm doing this today. I hope it's okay. Say we want to solve, it's also one of my favorite things, Tx equals b. But it is unsolvable. Oh no. there could be two problems. And the solution to these two problems will be two solutions. And I will call it the best of the best. And it'll be the pseudo-inverse. The pseudo-inverse will be the best of the best. But first, what are the two? So there's the best of the best. That's two things. So here are our two problems. Two problems. B might not be in the range of T. Oh, what's happening here? We might be in two different spaces. This will be important for data science. T maps from an inner product space V to another inner product space W. So these are two different spaces, okay? And that's why we're going to have two different problems. B might not be in the range. That's problem one. Problem two is that null of T might not be 0. Null of T is in V. Range of T is in W. Two spaces, two problems. We need two solutions, the best of the best. Okay. So what is happening here? If these weren't problems, so like if null of T was 0 and range of T was everything in W, then T inverse exists, right? And then solution is that X star is, this X star is my solution, is T inverse B. Fair enough? Yeah, Andrew.
So for this, would we say that B is in W or B isn't in W?
B is in W.
All right.
Otherwise, it doesn't make sense. Because T maps from V to W, so TX, well, okay, X has to be in V, otherwise TX doesn't make sense. And then TX has to be in W, so yeah. Of course, you're right that there would be an even bigger problem if B wasn't in W. Then not only do we not have a solution, our equation doesn't even make sense. But that very often people write down equations that don't make sense. So that's the third problem. We won't deal with that problem here. Okay. Good. I hadn't thought of that. Okay, so basically our solution is going to be that we're gonna do this. We're gonna say, okay, X star should be our solution. Will be T, and then I have no idea how to write this symbol. T dagger. B. And this is called the pseudo inverse. For an obvious reason, because I wrote it right next to the inverse, it's also called the Moore-Penrose inverse. Penrose is Roger Penrose, who won a Nobel Prize in Physics, one of the few mathematicians to win a Nobel Prize in Physics for stuff about black holes and cosmology and many other things. But you see, linear algebra is even useful in physics. Okay, so do we understand the setup and the problem so far? Okay, let's draw a picture, because pictures will help demystify this. First, we're going to draw a picture of W, okay? Because what you should think is that B is our data, and our data is noisy. It should be in the range of T, if not for the noise, okay? So now you're going to see the solution of our problem, of the first problem, is this vector right here. The projection onto the range of T of B. And that is 90 degrees. what's the projection onto the range of T of B? Sorry, it's this. Think of this as the range of T. And think of this as being W now. Just in a different space. In other words, how do you orthogonally project onto a space? So the orthogonal projection onto the subspace U of a vector V is going to be this. V, EJ, EJ, where the EJs are an orthonormal basis of V. Or another way to say this is that PU of V equals the little u, where V equals U plus W with little u in big U and little w in big U perp. In other words, what I want to say is that why did I make such a big deal out of this pink U O plus U perp, U direct sum U perp? Because it allows us to orthogonally project onto a subspace and get a unique answer. And so the fact that we can decompose any vector into two pieces uniquely means we can take the first piece. Does this make sense to everybody? So orthogonal projection is not some mysterious thing. You just take the first piece from this decomposition that we just did. That's the orthogonal projection. Again, it's back into the exact same picture. It's this. It's the same thing that we've been writing the whole chapter. You orthogonally project the vector onto a subspace like that. Okay? Yeah. So that's what we're going to do here. And the subspace is going to be the range of T. And this is going to solve our first problem. Our first problem is now solved because instead of doing Tx equals B, we're going to try to solve Tx equals orthogonal projection of B. Okay? Because now that's in the range. We have a chance, right? Okay. And now I want to say why it's the best of the best. So first, we're just doing the first best. What if I take some other U tilde? Can we call this U? Because we've been calling it little u. Can I call it little u? So remember, Tx equals B, that didn't work. So instead we'll do Tx equals the orthogonal projection onto the range of T of B. And we'll call this U. Call this little u. Okay. Now if we choose any other U tilde, what I want you to notice is that little u tilde, and B form a right, what's the next word? Circle? Quadrilateral? Triangle. It's the same triangle. This is our triangle for chapter 6, except here it's in green. Do you see that they form a right triangle? They do. It's this one. Do you see? I hope you can see. It's hard for me to draw this. I'm doing the best of the best that I can. I'm doing the best I can. Okay. Let's check that it's a right triangle. Well, no. Let's just use what that means now. U tilde minus B, that distance is greater or equal to U minus B. So this means that our best. This is the best. Our U, our little u, is the orthogonal projection of B. It is the closest possible vector to B. Of all the vectors in the range, it is the closest. This is what I want to show you. That's the first best. the best of the best, we're going to do this. This orthogonal projection is the closest we can get within the range to our actual data, B. Our data has noise, it's not in the range. Let's find the closest vector in the range to B. And why is it closest? Well, because this is a right triangle. So u tilde minus b squared, that is the hypotenuse. By Pythagoras, we get u tilde minus u squared plus u minus b squared. And what you do is if you ignore a positive term, you made it smaller. You've made that side smaller. And that is our theorem. We're almost done. You're going to actually understand the pseudo-inverse. You're halfway there. The pseudo-inverse is we're trying to solve Tx equals b, but we can't solve it. So we instead solve Tx equals to the orthogonal projection of our data b onto the range of t, because that is at least solvable. It's in the range of t, we can actually get there. Right? This actually makes sense. Did you think that the pseudo-inverse was going to make sense? Did it already make sense to you? When I first read it, it did not make sense to me. Okay, so I don't know. Maybe it's okay for you, but let's keep going. We're halfway there. We're halfway to understand. Now, what is the other? Well, we have to go to the other space W. Okay, so let's go to the other space. Or sorry, V. This is our space V. Okay, and somewhere in V is the null space of T. Okay, let's choose the null space. Okay. And then somewhere else in V is the orthogonal complement of the null space. Okay. Do you see what I'm trying to draw here? And so look, let me remind you, remember what we're doing here. We try to solve Tx equals b, but fail. Okay? So then we solve Tx equal to the projection onto the range of T of b. But, and here's the second problem. If n is in the null space of T, and Tx equals, okay, can we call this thing little u, because I don't, and Tx equals u, then look at what happens to Tx plus n equals Tx plus Tn equals little u plus 0 equals u. Now, hold on. You need to understand this piece. If I take anything in the null space and I have my solution Tx equals u, I actually have a solution. Like I found a solution x and Tx equals u. I'm so happy. And then somebody else comes along and says, well, here's another solution, x plus n. For anything in the null space. Do you see that I have infinitely many solutions? For every single vector in the null space, I get another solution, x plus n. Whatever my solution I found, x, just add something in the null space, that's another solution. This is an issue, okay? Imagine we're trying to solve Tx equals b, so then we orthogonally project and we solve Tx equals u. And somebody hands us the answer, and the first coordinate is 1,000,005. The second coordinate is 17 billion. The third coordinate is 18.2. We're like, oh, that's not too bad. The fourth coordinate is 54 billion. Okay, so that's a solution, but we might complain. right? What we would like is a reasonable solution. Okay? Here is the second best, or the best of the best, is we want to find the solution x whose size is smallest. We don't want coordinates that are 18 billion, 54 billion, 65 million. We want small, reasonable numbers. Okay? That's the intuition here. Right? So, in other words, here's the claim. What we should do to solve tx equals b when it's unsolvable, take my solution x star will be the pseudo-inverse applied to b, where the pseudo-inverse, I don't know how to write this, is what? We are going to, of course, orthogonally project onto the range. And after we do that, we are going to restrict T to the orthogonal complement of the null space. And we're going to invert that. And now we're going to stare. We are so close to understanding this ridiculous formula. This solution x star with this formula is going to be the best of the best in two ways. First, when you do t to x star, you will be as close to b as humanly possible. That's the picture that we already did with the triangle. Secondly, of all the possible bests in that sense, we will choose the one, this x star right here, has smallest norm. That I have not proved to you yet. This x star, with this definition, has the smallest norm possible. No 18 billion and 5, comma, 16 million, etc. Okay. So now I need to prove that to you. First of all, let's make sure this formula makes sense. This piece you're okay with, right? The first thing we should do to B is orthogonally projected onto the range so we have a chance. Okay. Then, once we're now in the range, I want to invert T. This is now possible if I get rid, remember what causes a map to be not invertible? It has a null space. The null space is the problem. The null space gives us 2 to 1 or 3 to 1 or actually infinitely many to 1. We can't uniquely invert because there's not a single element. This is that plus n that's messing things up. But on the null space orthogonal complement, there is no more null space of T. It's now injective. T restricted to this thing is injective. Is a bijection onto the range. But that's where we are already. We already went down to the range. And then T restricted to the null space perp is bijection onto the range. So we can just invert it. Does this make sense? Now, when you have the null space, you can choose many different direct sum complementary spaces. But what's going to give us the smallest norm is that we're choosing this one. That's why we choose this one. Do you know this? Like, if you just have, I should do it on the screen so you have it later. Remember from direct sums when we learned about them, a direct sum is not unique. Like, if you have this subspace through R2, let's call that U, you can also take W like that. And then R2 is equal to U O plus W. But we could also take a different W. We could take this W. Let's call it W tilde. And then equally valid, R2 is equal to the same U, O plus W tilde. So there are lots of choices for like the second piece. But there is only one choice when you do the orthogonal complement. This is U perp. And that is the choice that's going to give us the best of the best. Okay? And in this case, U is the null space of T in our application. Okay? So that's why we're going to do this. All right, I want to just pause for questions. I made you stare at this earlier. Did you have any questions? Should we prove the best of the best now? It's going to be another triangle. Okay? They don't have any other tricks. You take Pythagorean theorem and you ignore one of the squares, and that makes one of the sides smaller. Okay? This is the only thing I know how to do. Don't ask me to do any other inequalities, except if they can do that like that. All right. I hope there's a triangle. Let me see. So, first of all, this does make sense, right? We can invert T. It's a bijection. That part should, we could check it, but it should be okay. What I want to claim is that this has the smallest norm. Okay? So let's go over here. What I want to do is I want to choose this x star. Okay, my x star should be in the null T perp. X star is in null T perp. That is the x star which is chosen by the pseudo-inverse. That's the one. Okay? Now there are many other solutions. For example, I could choose anything in the null space. Like that pink N. And then I add it, and I get x plus n, or I get x star plus n. And x star plus n is also a solution, right? Like if I apply t to x star, I will get u. And if I apply t to x star plus n, I will get t x star, which is u, plus t n, which is 0. I will get u again. I will get the right vector again. So literally, I have, what you can think of is imagine this plane moving up and starting here. We have an entire plane full of infinitely many solutions stretching off to infinity where the coordinates are 18 billion, 17 million, 54. So, uh-oh. Do you see a triangle? I see a triangle. Is that the triangle? I don't know. Let's see. Let's think. What do I want to show? I want to claim something. I want to claim that x star has a smaller norm than x star plus n. For any n in the null space. Is that true? Yeah, because in other words, okay, let me write it out. X star plus n squared, that's the hypotenuse of this triangle. This is the n, and this is the x star. X star squared plus n squared. And that's Pythagorean theorem, and I can apply Pythagorean theorem because n is in the null space and x star is in the null space perp. They are 90 degrees to each other. So that really is a 90-degree angle that I drew. Because, like, why is this a 90-degree angle? Because I chose x star in the perp space. Otherwise it wouldn't be. So that's why. It's the best of the best. If I ignore this, I made the right side smaller. That's what I want. You take Pythagorean theorem, then you ignore one of the squares, so ignore, and that makes that side smaller, and I'm done. Wow. Yeah. Okay. Do you understand the picture in V, and do you understand the picture in W? Well, they both have to do with triangles, and they're both slightly confusing, but they're not that bad. Okay. I'll leave this up for a minute so you can stare and think. Ben?
Does it matter which direction you do it? Like if you do u minus u tilde or u tilde minus u?
No, it doesn't. That used to bother me. Because, yeah, what I really, like when I look at this, and this, and this, and this,
Yeah.
it doesn't matter, right? Because really when I look at this, now I've trained myself to think distance between u tilde and u.
Yeah.
So then it just, like, I just don't care which one. And it used to take up valuable mental resource for me of which one is, because you have to write down so many of these and you're like, oh no, I could make 8 mistakes.
Yeah.
Like there's two options. Okay, I guess I could make 7 mistakes, but there's 8 options. But no, none of them are mistakes. They're all the same.
Remind me where we got u tilde from?
I suppose, like, what if I took something else in the range, and I wanted to show that the distance from my original data was bigger?
All right.
Because I want to say that, look, projecting onto the range, orthogonal projection, that's the best you can do. And it's best because the distance between your actual data that you found and the thing you're actually going to produce is smallest. So, like, yeah, it's the best you can do. Like, B is not in the range of T, so we cannot solve Tx equal B. Like, that's actually maybe one of the most important things to realize. Like, the start of this story is important. We're trying to solve an unsolvable equation. It's unsolvable because there's noise that kicked B out of the range of T. We bumped the table when we were, measuring our magnetic field. I don't know what you all do in your science classes. You do something. Have you had anyone taken a science class? Is bumping the table a problem?
Or like for actually measuring like stuff in chemistry, it is a problem. Yeah.
What if somebody's bumping the table while you're trying to read like a millimeter? Right? That would be bad. Or if you're on a ship in the ocean. Okay. I don't know. One of these days I'm going to take a chemistry class at Lawrence when I have time. Meaning after I get tenure. I'll take chemistry. Okay. Is this picture okay though? This is it. This is 6C. There's nothing else really. This is the key. You need to understand this. Do you see the 2 problems? Do you see where the 2 problems are? The first problem is B is unreachable. It's not in the range. That's the first problem. The second problem is there's infinitely many solutions. If we had a solution, we could add plus n to it. And the n is a subspace. It goes on forever. We can get 18 million. Would you like an answer with one of the coordinates to be 84 billion trillion million? I can give you such an answer. Right? I'm not exaggerating. Like the null space goes on forever. So you can choose it arbitrarily down. So those are the 2 problems. B was not reachable. Then there was infinitely many solutions. The pseudo-inverse solves both problems. And that is why there are 2 maps in its definition. Orthogonally project onto the range makes our data reachable. This picks out the solution with smallest norm. using the nullity perp. Orthogonally project gives us the first triangle in that W space. The perp right here gives us another triangle in the V space. Do you see? It actually makes sense. Yeah. Oh, I really, really like the pseudo-inverse. Okay. Any other questions? Was there anything else in that section? I don't think so. Yeah. Remember, there's other, I mean, there was this picture. I hope you liked these pictures here. So remember, what matters is our subspace is finite dimensional. So and on Friday, I'll show you an application in data science where, we're in an infinite dimensional space, no problem at all. If our subspace is finite dimensional, we're good to go, right? And this is us trying to reach this red function by using a finite dimensional subspace spanned by 1, x squared, x to the third. I don't know how many degrees they go here. But it was okay, but it wasn't the best. Well, okay, so now here we get back to, remember your questions about, aren't there many inner products? How do we choose, which inner product should we choose? The answer is it's up to you. If what you care about is that your blue approximation in the finite dimensional space is really, really close to the red near this point, use the Taylor series. That corresponds to orthogonal projection with a certain inner product. Okay? But if you don't want that, if you would rather that your function, I don't know if you can see, you see there's a slight difference between the blue and red right there, slight difference right there. This one is an inner product that we take by integrating. So that's a different inner product. It gives you a different projection. And they're both valid, they're both orthogonal projections, but with respect to different norms, or different inner products. And so this one, the one that is formed by integrating the entire function, it gives you something that's good everywhere between negative pi and pi. Right? Because the integral cares about the entire region. Taylor series is caring about a single point. So this is kind of cool. This is calculus. But this is just the application, right? I guess 5th degree. Yeah. Find u in u such that v minus u is as small as possible. So this is our b, this is our data b, and this u is the thing we're going to find with tx. Tx equals u. And so the orthogonal projection finds the u that's closest to v. So we've been doing this. It looks like it's different, but it's the same. There's a triangle. Okay. Yeah, Andrew.
You did the other inner product with the integral with the e to the negative x, right? Added. Would that make it worse at the ends but better in the middle?
Yeah, so that e to the, like if you throw in an, yeah, so let me write out what you said, just for everybody else, make sure we're on the same page. If we do f of x, g of x, dx, that's what we were doing already. But if we throw on an e to the minus x, we can do that. It's still an inner product, because this is always positive, so it's not going to destroy positivity. But this e to the x has the effect of discounting the values really far away from 0. Because this thing shrinks down. So any sort of behavior really far away from 0 in positive x isn't going to matter very much. And by the way, the only time you throw on an e to the minus x is if you start integrating from 0 to infinity. Okay, this is called the Laplace transform. You go from 0 to infinity. If you went from negative infinity to infinity, this would blow up in the, e to the negative infinity is e to the infinity. That's going to be, you're not going to get a, right, we need this to give an actual number. So your integral has to converge. Yeah. But again, these are the things you have to deal with infinite dimensional spaces. But if you're careful, yeah, everything will converge. Don't worry too much about it. Or you just worry about it when it doesn't converge. Okay. Then you can ignore it. Any other questions? Are we okay with this section? I recorded this, so you can go back over. But yeah, I mean the key parts of 6C are this U-perp, really understanding this definition. You should be able to prove this. It's important enough to prove it, and inside of the proof is an explicit formula for that projection operator. And it also we did the trick that I said comes up a lot. I need to check that this is orthogonal to everything in U, but I'm going to do that by checking it on a single basis vector at a time. Once it's orthogonal to every single basis vector, it's orthogonal to every vector in U, because if you imagine replacing this by a sum of the Ci ej's, then we pull the sum out, pull the Ci's out, and every v minus u ej is 0, so we get a sum of zeros, and it's still 0. Okay. So if what I said didn't make sense, then come back to this later and think about it. I bet you'll be able to figure it out. But this is a key step. It's like something you can learn from this proof that goes beyond the proof. Once we have this, we know how to orthogonally project. And that means we can solve unsolvable equations. We orthogonally project to solve that first problem, and then we go to the null space perp to solve the second problem. Okay, so there's the pseudo-inverse right there. Right, and the way to think about it is like, look, if t was invertible, our answer would be x equals t inverse b. Okay, that solves tx equal b. But if t is not invertible, that's where we use this. Okay, I'm just repeating myself a million times, so I'm going to stop. These two pictures, yeah. I realize I know I already apologized once, but I'll apologize again. I lectured the whole day today. Not the whole day, because I did quiz you at the beginning. But I just think that I had a good, something really to add to the book in this case that was going to be helpful. So I hope it's okay. Friday, we will apply this to actual data. We're not just going to draw a vector B. I will literally plot a bunch of data points, and we will explain the pictures that I gave you on the first day of class. Okay? To prepare for class on Friday, just study for the test. Okay? I sent you an email that said, think about what are the most important things and study those. Do simple proofs. That doesn't mean like they're super easy, but they're important, right? And they're not going to be 18 steps with a bunch of tricks. They're going to be like, you need to know the definitions and take a couple logical steps from the definition to prove what you want. Okay? So when you're practicing, just keep that in mind. Okay? And you have the weekend to practice. All right. Thanks, everybody. 1 minute early.